Yeah, pretty much.
So, yes. Hello, who is this old man? So, this is the extent of my PowerPoint animation skills. You'll notice the default font and the default background. So we try not to get anything distract from the talk. So I always start with I always start my talks with a conflict of interests disclosure. If you go to any medical conference, you will find that all talks start with this. Psychology conferences, I presume many of you are psychologists, don't, and they should. You'll go to a big psychology conference, and quite often the keynote speaker will be getting paid $25,000, first class air ticket, suite at the Hilton, and they probably ought to tell you about that. So I am not being paid for this talk, but yeah, Sam's promised me a nice dinner later. I do not get funded by anybody. I've never been funded by anybody, and you cannot pay me to act as a consultant for this talk. Because again, when you see a keynote speaker at a major conference, they may well be charging Google $60,000, $70,000 to go and speak to their executives for an hour and a half. And when you have that kind of interest in your work, you're not rushing too hard to try and falsify it. Yes, my name is Nick Brown. I have a bachelor's in computer science and engineering from 1 million years BC. And then I went off and I was a computer guy, and I read my first scientific paper in 2011 when I signed up to do a master's, just too far from here. And one thing led to another. I spent a year in a psychotherapy school where I discovered what a terrible psychotherapist I would be. And I ended up doing my PhD in health psychology. And currently I'm affiliated with a Swedish university where I've never been, and I live in Spain. So yeah, I'm kind of everywhere. My first introduction to the wonderful world of scientific fraud was with this gentleman. Hands up if you know who this is.
I know his name.
Oh, you know his name. So this is Diederik Stapel, the Dutch scientist who was not the first scientific fraud to be caught. One of them are more prolific ones, but he was the first person to confess, because normally when you catch people committing fraud, they make up all kinds of dog ate my homework excuses, and end up 5 years later, you find them teaching high school mathematics or something. So during the year between when he was caught and when the final report into his fraud came out, Stapel wrote this book in Dutch, which it turns out one of my obscure skills is that I speak Dutch fluently, so I translated it into English. And yeah, this is a little quote from that book when he's wondering how he can improve his answers. And he says, how else did all those other researchers get those great results? Well, we're going to be seeing some of the ways in which you can get yourself great results. This book is available for free download. The slides will be available, and that reference at the that reference is a link to the free PDF download. So you will see some euphemisms both in the slides and in other stuff that we do. So a lot of the time we talk about error, and a lot of what you read is genuinely just wrong because people are incompetent. So we tend to talk about error, which avoids both embarrassment if it turns out to be a genuine error. It usually avoids lawsuits, although talk to me in the coffee break about that. So we say things like our tools help us to identify erroneously reported results, and any intention behind those is, yeah, it could just be massive incompetence, but a lot of the time it's fraud. So when you read a lot of fraudulent papers, you start to notice some features that are common. Still working, that are common to many of them. You'll find very high effect sizes. It helps to be able to look at numbers, even if the Cohen's D isn't reported, and say, what is the effect size there? Is that plausible in the real world? A lot of round numbers. I don't know why this is, but a lot of people who fake their studies fake having 30 participants per group or 50 participants per group, as if they're having to do their statistics with a slide rule or something. And they don't realize that if they just made it 48 and 47, it would look that a little bit more credible. And obviously, if you randomize 100 participants into two groups, 50-50 is the most likely split, but it's not particularly likely. Just because of the way the binomial distribution works. Lack of open data. Now, historically, we didn't publish our data at all. These days, not publishing your data is a bit of a red flag. And we're starting to see, because open data is becoming quite so popular, what we're starting to see now is fakers publishing fake data sets in the hope that nobody will look at them because they have to choose. Should we not publish our data at all? That looks suspicious. Or should we publish it so we look virtuous and then just kind of go, well, there's millions of data sets, probably no one will look at that. Unexpected patterns in the data sets, all kinds of repetitions that couldn't happen naturally. A particularly good one when people are faking data. Sorry about this cough. There was a story a couple of years ago from someone who was doing fake research in spider biology, and he was making up all of his spiders. And so he was making up the length of the spider, and then he was making up the weight of the spider. And so he was making up the weight by saying that it was the length multiplied by some amount and then plus or minus a small random number. And he was doing this in Excel. Unfortunately, he left the formulas in. So that's as close as we ever get to a smoking gun. So pro tip, if you are fabricating data using Excel, remember to go through and do paste special values to remove the formulas. Statistical inconsistencies of all kinds. Generally implausible methods. We'll see one or two of those coming up. Duplicated images, you'll be hearing from Elizabeth Spick about that, unless you did yesterday. When is Elizabeth on?
No, just not.
All right.
Maybe in the future.
All right. Anyway, duplicated images, Elizabeth Bick is the absolute queen of that. That's not so much in psychology, but a lot in biomedical. No reports of funding is another good one. Or ethical approval, although sometimes people just fabricate an ethical approval committee reference to the suitably long 12-digit number, and you think, oh, okay, that'll be the reference number of the ethics committee, and actually it's like the car registration number of the senior author. So today we're going to look at ways to detect certain kinds of statistical inconsistencies. So did you give people some background reading, or I mean?
No, this is all fresh to them.
All right. So nothing you're about to see is remotely complicated mathematically. You will be pleased to know. In fact, when we first published this, we thought it would probably get rejected for being trivial year 6 arithmetic. So, GRIM, great name. Not my name. Granularity related inconsistency of means. This is just a very simple technique for reading a paper, particularly in psychology, where you have a lot of integer data. So Likert scale data, percentages of people doing something. Not all mean values of integer data are possible, depending on sample size and rounding. So let's say we go to 7 people, and we ask them, how many children do you have? So we're going to get a total number of children, maybe 10, 11, 12, up to 18. And that's going to mean that, so for example, if the total number of children is 10 or 17, the mean will be 1.43 or 2.43. If they report having 11 or 18 children, that'll give us 1.57 or 2.57. This means that if you read that the mean number of children among these 7 people was 1.54, there's a problem. There is simply no integer which, when divided by 7 and rounded, gives you 1.54. Now, there are lots of, we'll come to some of the reasons why that might happen. This is intuitively obvious if you think, for example, of n being 5. You're going to expect the mean to be 0.20, 0.40, 0.60, 0.80, or 0.00, and you're going to notice 0.37. But it turns out, because that's the way the mathematics works, for any n less than 100, and we're always talking about 2-digit rounding here, this obviously applies to more decimal places if you have them. But for any n less than 100, when you have 2 decimal places, n% of correctly rounded to 2-digit means are possible. So here, n is 7, and there are 7 possible rounded means, and the other 93 are not possible. And it turns out that if you've got n of 41, there are 41 possible rounded two-digit means, and the other 59 are not possible. It's just not as easy to enumerate them sort of by looking and going, okay, n is 41, 2.37. Is that a valid mean? So you're going to need a little bit of help. So here is, we'll be using this later. There are many ways to do it. You can do it by hand. You can do it with this trivial, I think it's called an app now, but in fact, this is 3 lines of JavaScript running on a web page that will actually run on a Nokia pre-smartphone web browser. So many psychology papers have what we would call grim inconsistencies, means that are reported that cannot be correct, given what we know about the sample size. Now, these grim inconsistencies can occur for a variety of reasons. One is that, in fact, your sample size is twice as big as you thought it was because it's a 2-item measure. So you're getting the mean of 7 people's responses, but if it was a 3-item measure, that's going to behave as if it was a 21 item, n of 21. So that can, all of this is detailed in our paper about how to use it. Maybe some participants didn't answer one or the other question, but that should be reported. Sometimes, I'll skip this, but in SPSS, there is a curious double rounding phenomenon if you use SPSS. Sometimes we had one case and it was halfway values and the number was impossible, and we contacted the author and they said, oh yeah, they replied on paper and somebody circled both 3 and 4. So we coded that as 3.5. All kinds of other errors in reporting, or what we like to call, when we're being very clever and trying not to swear, proctonumerology, and I will let you work out the derivation of that term. So that's what we're looking for today. So with my colleague James Heathers, this is one of the better photos that I have of him. We wrote an article, and so we took 260 articles from leading journals. I mean, these are 3 of the top 6 journals in psychology, I would say. I read them all, worked out how many of them had statistics that we could check, so had sample sizes of meaningfully less than 100 that we could check. 36 of them, so half of the ones we checked, had at least one grim inconsistency in the reported statistics. That was too many. We decided to look at ones where we thought the inconsistencies were important. So we wrote to 21 authors and we got 9 data sets back. This is very typical to get less than 50% of data sets that you ask for. Going back 60 years, it's always been about that number. 2 of the refusal letters that we got from teams that had no authors in common were identically worded. I don't know if you can download this from buggeroff.I-won't-give-you-my-data.org or something, but it was quite strange reading those letters. All 9, once we got through the data set, we found the reporting errors and what had happened. One particularly good case, so at least 3 corrections were issued were really necessary. In one case, the author had done all the analyses in Excel, and they had managed to get the formulas wrong so that they had all of the records for condition 1, all of the records for condition 2, and below them, and then they were meant to have separate formulas for the means and the SDs. But there'd been an accident, and for condition 2, all of the entries for condition 2 were included, but as were all of the records for condition 1, and the mean and SD of condition 1 were also included. And the correction ended up being about 2/3 as long as the paper. That was quite spectacular. But of course, it is, as is traditional, it ended with, of course, this does not change the results of the article. Among the 21 papers, we know that two were absolutely certainly fraudulent. In one case, the author, shortly before we wrote our article, had left his university without leaving a forwarding address and deleted his Gmail. He'd gone totally off the grid, and I have 2 or 3 other papers by him that I know are totally fraudulent. So What I'm going to give you today is a little bit of history of Grimm, but you're going to be digging into it more in the workshop. So this is a very important man in the development of Grimm. This is a French teacher of statistics who publishes a lot of papers, Nicolas Guéguen from the University de Bretagne Sud in France, a very small university. He writes popular pop psychology books in the, well, he would call it evolutionary psychology. I would call it Benny Hill science. He has, shall we say, a somewhat old-fashioned attitude towards human relationships, as you will see. So here are some of his books that you can pick up in French bookstores. And so the first paper we looked at by this was published in the Scandinavian Journal of Psychology, which sounds like an obscure journal, but one of my psychological heroes, Jan Smedslund, once had a battle with Albert Bandura in the pages of this journal. So yes, here is the title of the paper. We insist that a men's behavior a few experiments. So I showed this yesterday to my daughter's boyfriend, who knows nothing about psychology, and he started laughing as soon as I showed him this. So the procedure was a female confederate, okay, so a researcher, with hair in one of three states. Her hair is in one of three, either natural or in a ponytail or in a bun, is walking along in the street and drops a glove in front of a carefully selected passerby who is the participant. So the dependent variable is the measure of the passerby's willingness to help, which is either like doing nothing or saying you dropped the glove or picking it up and giving it to her. Male, but not female passers-by were much more willing to help when the hair was in the natural flowing sexy herbal essences advert hair condition. Here's a sentence from the conclusion. Yeah. So we came to this because Neuroskeptic, a well-known blogger, tweeted about it, and I just happened to be talking to James that evening on Skype about a completely different matter. I pointed him at this, and we started looking at it. And so this is the table of results, and I've added n equals 30 per condition, which wasn't in the original table. And so as you see, the male pedestrians in the natural condition were rushing to help, 2.8 mean out of 3, whereas all of the others are fairly sort of anodyne numbers. And the interaction between male pedestrians and hairstyle condition, f of 8 on 2 numerator degrees of freedom, that's a pretty chunky effect size. Now, if you look, all of the means end in 0, which is quite interesting, with the n of 30 per condition. And so we started thinking, well, the numbers could be, maybe the data are very regular in order for all of these things to come out with a 0 at the end. Maybe there's lots of duplicate numbers in there. And also, I mean, there isn't that much possible variability simply because there's only 3 possible answers. And it turned out that with a little bit of work, we were able to reconstruct the entire data set just from the table of descriptives. This will not happen to you very often. So here's the table. And here is a copy of, now normally you would do this by columns, but I've done it by rows in Excel. And those numbers are the only numbers that will give you those means and standard deviations per row. And if you look, they are in groups of 6. This didn't strike us as being very likely. So, yeah, some spoilers here. The experiment never took place. You were probably surmising that. What happens is Gagin he calls himself a psychologist, but he doesn't teach a lot of psychology. He teaches introductory stats to first-year business and economics majors. So he teaches them about the chi-square test or about the simple ANOVA or t-test, and then he sends them out to collect data so that they can analyze it. And he's written this book, Statistics for Psychologists. That's what he does. But collecting data in the field is monumentally hard. I don't know if any of you have ever tried it. It is extremely hard. People do not do what you think they're going to do. So, in this particular case, the experiment was thought up by 3 female students who fabricated their data. And we know they fabricated their data because I have a witness from well, I'll come to that in a second. Here is, if you look at those numbers, you'll see the numbers in each condition. So these are the 0, 1 and 2. Well, sorry, 1, 2 and 3 conditions. All of those numbers correspond to what was in that Excel table. So they wrote this up. This is an actual page from the students' report that they handed in. This was then handed out the next year to students saying, this is something that people did last year. This is a really good example. If your work looks like this, you will get a good mark. So Gagin then stole these fabricated results and published them with his own name on and no other name, as if he'd done the work himself. Yeah, we have first-hand testimony of this. A whistleblower contacted us, sent us the documents, and he said everyone in the class made up their data. It was well known that they were doing it, and then the teacher would steal the ideas, pass them off. So I'm trying to think how many levels of fraud are involved here, because like the students made it up, the experiment never took place, and then the teacher stole the fabricated work and published it in a journal. We complained to the journal, which has not retracted the article, but it has an expression of concern on it, which is kind of a, yeah, it's a slap on the wrist that missed, really, an expression of concern. So yeah, you're welcome to. Okay, so now, this does not actually contain any grim inconsistencies. In fact, the only way that we were able to reconstruct the descriptors was by assuming that the means were correctly reported. What happened was, once we saw what this guy was doing, we thought, well, let's have a look at another of his papers. And that was where we started to discover that we couldn't. Replicating the full data set is always going to be difficult, but we couldn't even reproduce the means and the standard deviations. So in that particular case, there was a data set which the students had made up, 1, 1, 1, 1, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, 3. But in general, there isn't, and there's not even any data, so he has to make them up. So yeah, we started looking at other papers which did have grim inconsistencies, and that was where it came from. But just to give you an idea of how we started on the assumption that it was correct, which illustrates an important use of grim. Sometimes in a non-fraud context, you'll be reading an article and it'll say 90 participants were split into 2 groups, and they don't tell you how many in each group. But if you can see that the means are consistent only with 46 and 44 or 47 and 43, then you can proceed on that basis. And then you look at later results and you check that they're still consistent with 47 and 43. And if you then decide, oh no, that one's only consistent with 46 and 44. So this may or may not have been the second article we looked at. It was a very busy week, but this does illustrate the problem. Color and women attractiveness. When red-clothed women are perceived to have more intense sexual intent. We can see the theme coming back in. Although, anybody here consider themselves an evolutionary psychologist? Don't put your hand up. And it seems to me this is pretty much, evolutionary psychologists are going, well, what's the problem? So in this study, which did not take place, there were 120 males in 4 groups. Now, even if they're from your undergraduate pool, calling in 120 people and giving them a test is a fair old, logistical effort. And all that happened was they were given a picture of the same woman, and then in one of 4 colours of t-shirt, which I imagine were red, blue, green, and yellow. Well, actually, they are. That's on the results, isn't it? And yes, in the Benny Hill moment, participants evaluated the attractiveness and sexual intent of the woman. That was it. You get these people in, 120 of them. Here's a photo. Do you like her? Do you think she can give? Okay, you can go now. 20 seconds per participant, and they didn't do a battery of an hour and a half of right, yeah, sure. So 30 people per condition, and this is the table of results. And at this point, I was about to show you what's going on, but this is the first exercise in the workshop. So that's your jumping off point. All right, next is Sprite. Any quick questions about Grimm? You want a quick look at the advanced look at the workshop? Or we'll... All right. So Sprite is actually a piece of software. And you saw that table of Excel numbers that we were doing by hand to try and it's pretty tedious. You put a bunch of numbers in and you say, okay, the mean isn't right. So you make 1 or 2 of the numbers bigger until the mean gets right. And then you see, okay, the standard deviation isn't right. And you're doing a lot of it. So, yeah, James, I rather think the name came first. Yeah. But it describes pretty much what it does. So Sprite will produce possible distributions of input values given the mean, the standard deviation, the range, and a sample size. And it does this via a Monte Carlo techniques. It's not exhaustive, but it's pretty good. Once you've generated the data, you can download it. So if you want simulated data with an exact mean and standard deviation, you can do that. Of course, there are packages that do it too. And it's hosted by, is Daniel? Where's Daniel on?
He's on Thursday.
Okay, so Daniel Larkins, who you'll meet on Thursday, hosts it on his Shiny app server.
Oh, I think it might actually be viewing.
Yes, and it's also available in R by someone who took my code and made it a lot better. So this is what happened when we did the Gauguin 2015 analysis by hand. So you can see here, actually here there are a couple of things that are not quite right yet. So imagine that we're most of the way through, and you'll see here that the mean is 1.77 and not 1.8. And the standard deviation is a little bit too high. And if we replace that 1 with a 2, then it works. And so that's how you do it. You look at the numbers and go, oh, okay, the mean's too small, make one of the numbers bigger. And then magically it turns out that you do hit the SD. Sometimes you overshoot. And then sometimes it turns out you can't produce that standard deviation. Here's another one. The mean is okay here, but the standard deviation is a little bit too high. And so you can reduce the dispersion by replacing the 1 and the 3 by 2 2s. So the mean stays the same, but it's quite amazing that standard deviation goes down by 10% just by removing 1 pair. And basically, Sprite just does that very, very fast. And if we put that Gauguin 2015 paper into Sprite, the one where I told you there was only 1 solution, Sprite will draw you the distribution. So here are 6 1s and 24 2s for that particular mean and standard deviation. And it will tell you, I asked it to try and find up to 4 solutions. It only found 1. It's not perfect, but generally speaking, if you ask for 4 and it only found 1, there aren't 17. And then this is another, so slightly more complex from the same paper, because the mean is a bit more reasonable. But again, it only found 1 solution. and you'll be playing the sprite later. So Sprite's has a couple of uses. One is just as an educational tool. When you see numbers reported, what does that probably look like, or what could it look like? And you just simulate as many of these as you want. So, for example, here's some fairly basic data with a mean. So 1 to 9 scale, mean is 4.8, so somewhere in the middle, standard deviation of 1.7. And already you can see there probably aren't too many extreme values. Now, this is not something you can put in front of a court of law. There is actually a complete solution. Somebody wrote a program to generate the complete solution rather than just random exploration of the sample space. But if you've got an N of 1,000, you're going to be borrowing the Met Office's supercomputer for the weekend. Whereas, for example, so that's with the SD of 1.7. If you just change the SD to 3.4, you're going to get this, because in order to have that amount of dispersion, and note the standard deviation is bounded at half of the range. So the standard deviation cannot exceed 4, or perhaps 4.01, depending on how you calculate it. So which of these is more plausible? Well, it depends on the research question. If you ask people how much they prefer chocolate over strawberry ice cream, it might be reasonable to get data like that. Maybe not too many people are super passionate about it. If you ask people what they think about Donald Trump, you would expect something a lot more, I think, like that. Although actually social science is weird. So there's a sort of, I would call it like the sort of the noise version of the central limit theorem. You know, people still manage to sort of go, not sure, you know, are you on? Okay, so there's a few caveats with Sprite. One is, yeah, it's a heuristically driven process. It's basically random numbers trying to explore the space. There is no guarantee that it will find a solution if one exists. But in practice, with Likert type data or even age, participant age data, and a sample size that isn't, you know, completely off the scale, it will generally find you quite a few solutions, and you will get a quick idea of what the data probably looked like. So yeah, it's not bad. Don't, on the basis of Sprite, go and stand on the street corner and shout that someone's a fraud. But it really helps sometimes to think about what the data might look like. So yeah, here is the complete solution I mentioned, called CORVIDS, which is another terrible acronym. And that actually will go and see if there is a solution mathematically, given enough compute time. And yeah, as I said, the results always require interpretation in the context of the study. But you should. I mean, it's the learning process and the forensic process are kind of mutually reinforcing. You have to start off looking at some things that you're a bit suspicious about, and then go, okay, why might I be wrong about this, and what distributions make sense? Right. And then, right. Any pressing questions about Sprite? Sorry. Oh, I mean, 500 is usually okay. You'll see when you get to play with it, you know, put some big numbers in. Actually, it's going to be fun when everyone's playing with it on that. It'll test that server out a little bit, but the kind of things you're likely to come across in most social science situations will usually give you you'll get some solutions. Occasionally, you might have to wait 30 seconds. But you can also ask it for 1 or 4 or 9 or up to 100 solutions. So if you ask for 100, it's going to take longer. With that?
With a clean data set, you can generate but you can simulate the mean and standard deviation.
Yeah.
You'll generate the value.
P-values downstream of this. We're just generating data here.
So doing with sort of matching up to a particular value. But I'm thinking about within subject data set where despite the fact we have correct mean standard deviation, have correct correlation between.
No, this is purely generating static data. Yeah. Yeah. I mean, within two words, grosso modo, as we say in French, within very roughly within subjects, data is essentially difference data. So I suppose you could generate mean and SD of the differences, but Sprite it just generates piles of numbers. What you choose to do with those after that is up to you. All right. So rivets is the third topic. I'm kind of glad Sam asked me to do this because I haven't presented on this before, and it is not going to be something you're applying very often, although the day when I finally used it to get and it worked, I was somewhat punching the air. But using it is quite educational, and understanding how it works will improve your ability to read papers. So yes, it's an idea I had, and a bit like that first Grimm example that didn't have any Grimm errors in it until we got to the later ones by Gay again. This is based on a misunderstanding. So yeah, this is my acronym, and it's just as bad as Sprite, but it says if you use rounded input test variables, you should not get exact test statistics. And the idea of rivets is to detect results that have been fabricated without data, which is to some extent what Grimm does. So here is a paragraph that is, or sentence. This is actually taken from the rivets preprint, except that I've introduced a small error in it. So yeah, this is from the Journal of Porcine Aviation Potential, aka Can Pigs Fly? And so here are the results of the effect of flying versus being transported by drone on pigs' appetite. And so we have 55 self-piloting pigs, 53 drone-transported pigs, and we have a t-test. We have a mean and a standard deviation and a t-test. And so imagine that I'm reading this paper very early on in my scientific career, and I decide to check that t-statistic. Not an unreasonable thing to do. So I go to my little online calculator. You can also, these days I have a spreadsheet that does it. Obviously, it's not very difficult to do. And so I enter those mean, standard deviation, sample sizes, click calculate now, I want an unpaired t-test, and I get this result. And I get a t-statistic of 4.16. Whereas the article said 4.19. I got very excited. I thought, they are cheating. So is that a problem? Well, no, because the numbers that went into those t-test calculations were not 4.53. They were some 64-bit number inside a computer. So, for example, that mean would have rounded to 4.53. That standard deviation, that other mean, that other standard deviation. And when you put those into the calculator, or you actually get this, 4.19. In other words, there are lots of different numbers that can round to those input numbers and will give you a different test statistic. So here they are, here are those results. When I put in these numbers that you saw on the last slide, I get that, and there's my 4.19. In fact, I got the problem completely wrong all along. The issue is not that the t statistic doesn't match what you get from the calculator. Because starting off from those rounded numbers results in a loss of precision, we should expect that quite often the t statistic, and there are other, this also applies to a surprising range of other statistics, will not exactly match what's reported. In fact, when you have only results that match the rounded input variables, that's when you could be having a problem. Because if I sat down one morning to make up the entire study, I would make up the mean, I would make up the standard deviation, I would put it into that calculator, and I would come out with that exact t statistic. And I sat on this idea for quite a while until I was investigating this paper. And so it's about, forget what it's about. Race is involved somewhere. This whole affair was quite a big scandal. The guy was doing, as a criminologist, doing research into effects of racism, and he was really not doing people of color much of a favor by making up all of his numbers about them. So here is a table of, these are not from a t-test, these are regression coefficients from multiple regression. So here is a t statistic, which, as we all remember, t statistic of a regression coefficient is the coefficient divided by the standard error, is it not? And you can see visually that's not too far off. That's like 0.9 times about 20. It's going to be about 0.49. So we get our calculator, little screenshot from Microsoft Calculator. Well, look at that, 0.941 divided by 0.019 is 49.526, exactly what he had. But the possible range, do this by hand, the possible range of t statistics that would match, that you can make with coefficient and SE that round to those numbers, it's that range, and there are 2,662 possible values, and he just happened to get the one that exactly matches the rounded input values. And then we look at the next one, and exactly the same thing happens. And exactly the same thing happens on every other number in that table and in every other number on the next table. The next table had problems as well because quite a lot of the numbers had just been copied and pasted from the previous table and had different results, different labels put on them, but that's so in the rivets preprint that we wrote, we explain why you have to be a little bit careful in using this, and you'll see there is an example. But with every single one of these numbers coming out like that, plus so much other stuff surrounding this paper and half a dozen other papers by the same person, this was I was quite pleased that we found this this example. So you won't come across many of these, but it's a thing to know. So yeah. To conclude, why study this stuff? And I would hope maybe Michelle would agree with StatCheck and one or two other things. First of all, just playing with these numbers all day, or for an hour in a workshop, but all day, will deepen your knowledge of basic statistics. It will make you better at reading papers. Particularly if you come to a field like psychology or sociology without a whole lot of mathematical background, you tend to spend most of your undergraduate time reading the introduction and the literature review and the discussion, and you tend to be not terribly at home in the results section. And the methods, the second half of the methods, where they tell you how they analyze the data, and the results section are where it's actually all happening. And so the more you study this kind of thing, which is, I mean, it's fun because you quite often, you will turn up so many, mostly false alarms, mostly not fraud, but you'll turn up things going, oh, that's an error. And you write to the authors, you know, you think, okay, that looks like an honest error. Write to the authors and they'll say, oh, yeah, you're right. We forgot to report that we dropped a participant. And should we issue a correction? No, it doesn't really matter, but it's fun to know. And you're playing around. And so it will, a lot of people have, in my experience, a certain amount of fear of digging into the methods section, these waves of numbers and T and R and P and Cohen's D and all of these things washing over you, and it will make you more at home with those. Sometimes you will actually find real fraud. There's no way around that. There is a lot of it about. More often you will find honest error by the authors, but you will sometimes find real fraud. And even more often, you'll find that you've made a mistake. Which paper? Yes. It's been retracted. He's had 4 or 5 papers retracted. He got fired. It was a pretty big. It was the biggest scandal in American criminology for 50 years. So, yes, it's always nice if you already know a paper is fraudulent. At that time, we suspected it was, and this was kind of one of the nails in the coffin of that paper. Even more often, and especially when you start, you will find you've made a mistake, and you will find that you have not read the paper correctly. For example, with Grimm, you'll discover that you didn't. Not spotting a multi-item measure is an absolute classic. And you can still use Grimm on multi-item measures, but it just increases the effective sample size. So sometimes you go over the 100. If you have n equals 30 and 4 items, your effective sample size is 120. And really, yeah, rejoicing in your own fallibility is a key component of happiness. It's taken me a while to get to that realization, but here I am. I'm 63 years old, and I'm kind of more at ease with my fallibility now than I used to be. And so here are some references. And so I put my Blue Sky account on the bottom of every slide, but in fact, I'm still more active on Twitter. It's still limping along. There's my email address. I have a blog. I haven't written anything on that for several months. Here is my Google Scholar, if you want to see some of the. I have a paper about to be accepted with Andrew Gelman, who is probably. Do you remember in the run-up to the general election, they were talking about MRP polls, which are a particular. Yeah, Gelman invented MRP polls, and I've got a paper with him about to be accepted, which is just ludicrous. But one of the nice things about academia, universities are very hierarchical places, but academia itself is extremely flat. If you write to people about their papers, they will write back to you, unless you say you think they're fraudulent, and then they tend to. Right. All right.
Brilliant. Thank you so much. Right. Do we have any questions from the floor? Let me just go over to our virtual audience.
There'll be someone in the chat 45 minutes ago going, "Can't hear."
Yeah. Yeah, you're just being frozen.
When I drop the.
Okay, so we have the next one. How do we? You know what those questions are, Alex? Okay, one second. Yeah, thank you. Okay, you want to tackle those?
Given how simple data simulation is becoming, will techniques like Sprite and Grimm only be useful for old paper? Well, none of these would be necessary if everyone shared their data. So everything you're doing here is because you don't have the data. On the other hand, until data being shared in places where you can download it without the authors knowing you've downloaded it, becomes the norm. You'll still perhaps sometimes be doing analyses of the paper to determine whether to ask the authors for the data. So, I mean, an extension to that question that we sometimes get asked is, aren't you just teaching people how to best frauds? And I guess the answer is yes, but the majority of people who go in for scientific fraud do so because they're not very good at the basic science anyway. So they're not going to learn sort of some of these techniques because they pretty much flunk statistics, and they just, they know that if you they copy papers and just fill in different numbers. So Startle, for example, one of the ways he got caught was he was using the same data set across multiple papers and just relabeling the variables, because he knew that in this data set there was a difference of a certain statistical significance between the two groups. And I asked him once, look, why didn't you at least kind of just, add one to some of the numbers and take one off some of the other numbers? Wouldn't have changed the mean or the standard deviation very much, but at least the number. And he said, well, I'm not very good with computers. But there is a chance that rounding errors like that last one are not malicious, just stupid. They could have copied over the round values. It's true that if you are the kind of person who runs SPSS on your real data, and instead of taking the coefficient, the standard error, and the t-statistic from the table, you could copy over the standard error, the coefficient and the standard error, and then decide by hand to recalculate, even though they were in front of you in the table. However, we're kind of getting to the extraordinarily unlikely level. I don't know if any of you have ever been a 7-year-old and had to lie to your parents about some particularly egregious thing that you were guilty of, and you made up some story that involved a spaceship or 3 dogs running in, and yes, but nobody would ever do it that way, is the answer. Back in the days of slide rules, yes, absolutely possible, because you would do whatever it took to calculate the standard, the regression coefficient. Probably, or in the days of early 1970s Fortran programs, and then you would do whatever it took to calculate the standard error, and then you would write them down, and then you would. But these days, all of those numbers are right there, on a plate for you. In fact, if you did it by hand, you'd make transcription errors. There are literally no transcription errors in that table. So it's potentially possible, but only if you are if you were the kind of researcher who did that, you should be handing back your PhD anyway, because you're throwing the precision away. So it doesn't, yes, it's possible, but nobody would ever do it that way. There was another problem with the Stewart data. Somebody noticed that none of his rounded numbers ever ended in 0. And he said, yes, when a number ends in .0, or 300 or 400 or 450, the last digit of a whole load of 3 decimal place numbers, there should be, 10% should end in 0. And none of them did. And he said, yes, when I see a number ending in 0, I just add a 1 to it, so that it doesn't accidentally get truncated by the software, taking off the. And it's like, well, first of all, that's obviously not true. And secondly, if you did it, you've just changed the data. Yeah. So it's a question of whether people want to admit to the fraud or pretend to be so monumentally incompetent that I think I'd be less embarrassed to admit to the fraud, which is what startled him.
Did he have 20% ones?
He had a look. It was just. We see this also, for example, with people who have fabricated a study and then claim to have lost the data when their laptop was stolen. Because despite the fact that these are 35-year-old people who have grown up their entire life with computers, apparently, and they got a $5 million grant, at no point did they think, it would be a shame if we lost the data. I'd better go and spend $3 on a USB stick, or perhaps connect a Google Drive account to make automatic backups. And so again, these people, they're fabulous scientists. They should definitely get an early career superstar award. They should definitely get a lab and a grant to run 15 people, but they don't understand the most basic workings of a computer. And this is just simply, as I say, either impossible, because they're lying, or represents a level of incompetence that we would have noticed, that people would have noticed about them, because nobody is only incompetent. Nobody on the age of 85 or whatever is that incompetent with a computer and yet able to produce, scientific output. So it makes no sense. But it's the people, when you confront them, when you confront fraudsters, they all react in very, very, very similar ways. And that was what made Startle so unique. And although I'm playing my own trumpet because I translate it, I do recommend the book because it's not a 100% candid confession. There are things that he has changed, I believe, to somewhat reduce the scale of the fraud, but it certainly isn't a denial, and he doesn't blame anyone else. So I do recommend that too. It's in the references. Hold the microphone closer.
Yes. Thanks, Nick. Are there any other questions? I don't think virtually anyone in the audience.